Hello class, this is section 4.6, which is modeling with exponential functions. So when you're modeling with exponential functions, you want to use this generic function, which is q of t is equal to q sub 0 e to the r times t, where q represents quantity. You could also use m for mass or p for population, but it doesn't matter. The sub 0 means initial amount, so this is the initial amount. R is the growth or decay rate, and T is time. So for this example, it's a gray squirrel population was introduced in a certain county of Great Britain 30 years ago. Biologists observed that the population doubles every 6 years, so that's key. It doubles every 6 years. All right, now the population is 60,000. What is the initial size of the squirrel population? So we're looking for this, the initial size. That's what we're looking for. So we know that the population doubles every 6 years. So that means the quantity goes from 1 to 2 every 6 years. So it starts at 1 and it doubles every 6 years. So I plugged in 6 for t. So we got to solve for r. So we don't really need the 1 for now because it's just 1. So what we can do now is take the natural log of both sides. So let's take the natural log of both sides. I'm going to create some space here. So the natural log of both sides will allow us to solve for r. So that's going to be ln of 2 equals 6r ln of e. But remember, ln of e is just 1, so that goes away. And to solve for r, all we got to do is divide by 6. So r is equal to natural log of 2 divided by 6, which is approximately ln of 2 divided by 6 is 0.1155245301. You don't want to round because if you round, you're just compounding your rounding error. So you don't want to do that. So we know what the growth rate is. This is your growth rate. That's your R. Now we can go back and answer this question. It says, and now the population is 60,000. That was 30 years ago. So when t is 30, the population is 60,000. So we can write a new equation. The population is 60,000. We don't know the initial population, but we do know the growth rate is 0.1155245301. And we also know that time is 30 years because they tell us that the population is 60,000 30 years ago. So t is 30, the population is 60,000. We need to solve for that initial amount, which means we have to divide both sides by e to the 0.1155245301 times 30. Both sides. And so q sub 0 will equal, if you type that into your calculators, 60,000 divided by e to the that long decimal times 30. I'm getting exactly 1875. All right. Which is exactly the right answer. All right, estimate the population, the squirrel population 10 years from now. Well, 10 years from now, we have to add 30 plus 10 in order to get t equals 40, because that would be 10 years from now. All right, so when t is 40, we want to know what the population is. So let's do this. So it's going to be q of 40 is equal to the initial amount, e to the 0.1155245301 times 40. If you type that into your calculators, you should get getting 190,488 if I round to the nearest whole number, and that is exactly right. All right, going down to this problem, the half-life of radium-226 is 1,600 years. Suppose we have a 22 milligram sample. So that's your initial amount. So that represents m sub 0, and they're giving us the function that they want us to use. H stands for half-life, which in this case is 1,600. So we have m of t is equal to the initial amount times 2 to the negative t over 1600. So that is the answer to the first part. For the second part, they want us to use a different model, this model that we used up above. Notice there's a negative in front of the r. That just tells you that it's a decay instead of a growth. So to find that, we already know m sub 0 is 22. We need to find the decay rate, r. So in order to find r, we're going to have to first figure out what the half-life is. Actually, we can just say the half-life is 1600, so that tells you what the time is when when 2 becomes 1. So one, if you start off with 1, that's double. We got to do this backwards because it's half-life. You're starting with 2, and 2 becomes 1 in 1600 years. So this is how we're going to find R. You're going to start with 2 milligrams, and it's going to become 1 in 1600 years. So now we need to solve for R, and we can do that by dividing both sides by 2. And then taking the natural log of both sides, bringing down that amount, which is ln of 1/2 equals 1600 r ln of e, which is just, of course, 1, which we don't need to write. And now we can divide both sides by 1600. So r will equal to the natural log of 1/2 divided by 1600, which is, so you should be getting negative 4.33 e to the negative 4, which means that's scientific notation. That means move your decimal 4 spaces to the left. 1, 2, 3, 4. So there's going to be 3 zeros after the decimal. All right, and so now we can do part A. Now that we have all the information that we need. Actually, we are doing part B. So I think we have everything we need already. So the initial amount is 22. We have R, negative 0.000433 t. That's our model. And that is exactly right. So now we're ready to move on to part C. How much of the sample will remain after 3,000 years? All right, so after 3,000 years, we got to see how much of the sample remains. That just means that t equals 3,000. So let's go ahead and use the model that we just came up with. M of 3,000, substitute 3,000 into t. So let's see what we get. 22 e to the, that long decimal, times 3,000 is, I'm getting 5.99. They want us to round to 1 decimal place, so I'm going to get 6 milligrams if I round to 1 decimal place, 6.0 actually. All right, after how many years will only 19 milligrams of the sample remain? So only 19 milligrams remains. That means 19 is the remaining amount. And we're starting off with 22, and we want to know what the time is. So we're solving for t this time. So we first got to get rid of that coefficient, 22, divide both sides. I'm going to create some space by erasing this. Now we have 19 over 22 equals e to the negative decimal times t. Take the natural log of both sides. Bring down your exponent. Now we have natural log of 19 over 22 equals negative 0.000433 t, ln of v, which disappears. And now we just divide both sides by the decimal coefficient. T is going to equal whatever that gives us. So on the calculators, natural log 19 divided by 22 divided by negative 0.000433. I'm getting answered round to one decimal place, so I'm getting 338.6. 338.6. Let's see if that's right. .4. That's because I didn't use all the decimals. Once again, I'm cutting it off at 4.33, but you should actually write the entire all the decimals that show up on your calculators. So I'm rounding, which is not what you're supposed to be doing. That's why I'm slightly off by a couple tenths. But if you use all the decimals, not just these that I'm using, then you're going to get the exact answer, or the answer that they have. All right, a wooden artifact from an ancient tomb contains 65% of the carbon-14 that is present in living trees. How long ago was the artifact made? So we're looking for time. So that's what we're looking for. All right, 65% remains. That means 0.65 remains. They tell us the half-life of carbon-14. So because they tell us the half-life, I recommend that we use this formula. Or is it? Actually, we don't need to use that formula. This one here. Yeah, we could. I mean, let's just do it the way without that formula. All right, so here we go. So let's see. We need to say that 0.65 remains. Do we know the initial amount? Well, we don't really need to know that. It's going to be e to the 5730. That's the half-life. Times r. Actually, we do need that formula. Sorry about that, guys. We need this formula. So here it is, this one. So m, let me copy it down. Okay, so we know that 65 remains, and let's see, the t is the time, which is, I'm sorry, that's half-life. So t, that's what we're looking for. We're looking for t. The half-life is 5730. So what we can do is we can take the natural log or a regular log. I'm just going to take the natural log since that's what we've been doing. And then we can bring the exponent to the front. So we have natural log of 0.65 equals negative t over 5730. And then the natural log of 2. This time these do not disappear because this is not an e. If this was an e, then this would have became 1. But since it's a 2, it has to remain. So what we can do at this point is divide both sides by that. Natural log of 2. Natural log of 2. And also multiply both sides by 5730. Or actually negative 5730. So we can cancel the negative and the denominator at the same time. And so now we have t equals negative 5730 natural log of 0.65 over natural log of 2. And that should do it. Type that into your calculators. And I'm getting 3561. Do they want us to round to the nearest whole number? Yep, 3561. And that's exactly what the answer is. The last problem is about Newton's law of cooling, which states that, well, this problem says a hot bowl of soup is served at a dinner party. It starts to cool according to Newton's law of cooling so that its temperature at time t is given by this function, where t is measured in minutes and big T is measured in degrees Fahrenheit. What is the initial temperature of the soup? Well, the initial temperature means that time is 0. So if we plug in 0 for t, we get little t, that is. Well, this is just going to become 0, which is 1, right? Anything to the 0 power is just 1. So you're just going to add 57 plus 133, which is what? 190 degrees Fahrenheit. That's pretty hot. All right, what is the temperature after 10 minutes? So after 10 minutes, that just means that T is equal to 10. So T of 10 equals 57 plus 133 e to the negative 0.05 times 10. All right, so let's do that. I'm getting 137.66. Round to one decimal place, so 137.7. All right, after how long will the temperature be around, will be 100 degrees Fahrenheit? So the temperature, we want it to be 100. So now we need to solve for little t, which is the amount of time in minutes. So in order to solve for little t, we first have to subtract 57 to both sides. So that would be, what, 100 minus 57, I think is 43. Yep, 43 equals, 133 e to the negative 0.05 t. Divide both sides by 133 to get rid of that coefficient. And then we have 43 over 133 equals e to the negative 0.05 t. Now we take the natural log of both sides, bring down the exponent, so we're going to have natural log of 43 over 133 equals negative 0.05 t. The ln and the e cancel out, and our final step is to divide by the coefficient. So t is going to equal whatever we get. So natural log of 43 divided by 133, close parentheses, divided by negative 0.05 is 22.58. They want us to round to the nearest whole number, so that's going to be 23. 23 minutes. And that completes this section.